The broadcast is now starting. All attendees are in listen-only mode.
Hi, good evening. My name is Dr. Samir Puri. I want to welcome you guys to this webinar. Today we've got a great informational webinar planned on the new VITA Enamic material. Joining me today on CerecDoctors.com is Dr. Russell Giordano, and he's kind of the guy who thought of this concept and kind of created this material. Before I introduce Dr. Giordano, I just want to let you guys know we've got a lot of videos on Enamic already. We've got some clinical cases and some great discussions going on CerecDoctors.com. If you guys will go ahead and visit www.cerecdoctors.com/VITA, you can find videos as well as discussion threads relating to this particular material. So we will be taking questions. You can type in your questions as we start the webinar, and we'll do our best to get those questions over to Dr. Giordano so that he can address as many as possible. We've had about 500 people register for this webinar, so there's a lot of you online. So if we don't get to all the questions, we will certainly do our best to address them after the fact on the discussion forum. So without further ado, let me introduce Dr. Russell Giordano. He's an associate professor and Director of Biomaterials at the Boston University Goldman School of Medicine. He also is an Associate Professor in Material and Science Engineering. He directs numerous research projects on a variety of dental materials. He got his DMD certificate in prosthodontics at the Harvard School of Dental Medicine and is a Fellow of the Academy of Dental Materials. And he's been working on the development of the CEREC VITA Block Mark II at MIT as a postdoctoral student since 1987. So he's one of the most knowledgeable guys when it comes to CEREC materials. He lectures nationally and internationally and serves on the editorial board of several journals, including the Journal of Dentistry and the Journal of Biomedical Materials. And he's an active in the development of U.S. and international standards for dental materials, as well as the chairman on the ADA CAD/CAM Standards Committee for Zirconia, and serves as the U.S. expert on dental ceramics. So quite a resume. It is my distinct privilege to introduce Dr. Russell Giordano. Russell, take it away.
Thank you very much. Thank you for everybody for joining me tonight. Well, tonight over here in Boston. So I'm going to be talking about properties of the material, comparisons to some other materials that are still available for you to use, why this material is unique, and then show some cases that as well using the material. So the trade name is Enamic. It's called a hybrid ceramic. So this is a transilluminated block over here, and this is a stained crown over here. This is what Boston looked like a few weeks ago. We've had lots of rain. Today was a monsoon, but this was from our blizzard with 30 inches of snow. Those are some cars over here. That's me after snow blowing the driveway, our ocean front. And this is what it looks like when it first starts. Really beautiful, and then it doesn't end up so beautiful at the end. So I've been at the Goldman School of Dental Medicine for about 20 years now. The school itself is actually celebrating its 50th anniversary. So there are a number of events that are ongoing throughout the year. We'll be having a digital dentistry symposium sometime in the fall. We haven't specified the dates yet, but I'm helping to organize that, and hopefully that will be some interest to everyone here on the webinar as well. So Sam already talked about most of this, so I don't have to talk about it. I've just been involved in CAD/CAM materials for a very long time. I was lucky enough to start working on the development of the Mark II block when I was at MIT and at Harvard, and really been also lucky enough to work with many of the CAD/CAM systems, starting with the CEREC 1 system. Still waiting for an OmniCam, however, to get at the school. So this material was actually ended up being a cooperative development between VITA Zahnfabrik over in the small town of Baden-Sachsen in Germany and Boston University, and it was a material that was developed by me in the lab at our Department of Biomaterials. We patented the material, and VITA was the company who decided to license the technology, and we spent a number of years working on it. VITA is a very careful company, essentially all the testing that was done in triplicate by me at the school, by VITA, and then VITA contracted with a number of independent universities in Europe, primarily Germany, to also do testing. And we didn't tell each other what was going on until we presented all the results to VITA. So it was a good way of double checking everything that was being tested to make sure that there wasn't any bias in anybody's testing. I'll show you a lot of data from Europe, some data from ourselves, and some data from VITA internally, as well as some data that we incorporated from other companies like 3M or Ivoclar into the comparison part. So this is the research team at the end here. Dr. Anna Boyle-Miller, who ended up directing the project toward the end here. Kathleen Clem, who provided lots of information. She's a dental technician. Myself, Dr. Teal, who was responsible for developing the Mark II material, and Mark II really helped cement CAD-CAM, keep the CEREC system going, since there really weren't any materials that were designed for the system when it first came out. And then this is Andrea Coldeo, who's actually doing her doctorate as part of this project, because this is a really unique material. So the most famous monolithic material, when I think of it, is the monolith from 2001: Space Odyssey. We're supposed to have the music here, but we have some audio difficulties with my computer. But monolithic materials really started many years ago, 25 years ago or so, with the VITA block up here in the corner. And we've had blocks like the Real Life being developed and on the marketplace. We have Emax, Zirconia, Lava Ultimate, and the last material is Enamic. And Enamic is different than any of the materials that you see here. It's not a traditional composite resin. It's not a traditional ceramic. It's in between both of these materials to try and take the best properties of a ceramic and the best properties of a composite resin and put them into one material. So it's not a composite resin, it's not a Lava Ultimate knockoff, and it's not another Mark II material. It's completely different. The idea was to try and create a material that would have advantages of a ceramic, such as color stability, stiffness that would be close to that of a natural tooth, wear resistance, but also combine that with the advantages of composite resins. And composite resins traditionally have been looked at materials that are very wear kind. They're resilient. I mean, they tend to absorb energy and can flex without failing. And that's not something that a ceramic can do. The disadvantages of the ceramic is that it's brittle. So even though it can be very strong like zirconia, it's still a brittle material. If it starts to flex, it's going to crack. Zirconia has some more resistant properties to it, but it's going to crack if it starts to flex. And everything in the mouth tends to flex. There's a lot of interesting studies on jaw flexure during chewing and opening, and some issues in some papers looking at what happens when we join implants together with an inflexible material. But ceramics don't flex, they break. They've traditionally had issues with wear of the opposing dentition. At the dental school, we have lots of patients who come in. The classic case is the patient has a maxillary bridge with lingual porcelain and old porcelain material, and they basically completely destroyed the lower anteriors. You've got wear through the enamel at the dentin, and that's a difficult thing to fix. So we didn't want to create materials with those properties. Ceramics tend to have lots of chipping when they're being milled. Composite resins, the traditional things that we think about problems with them is, one of them is color stability. The color in a composite resin is primarily developed with the polymer. And as the polymer is subjected to light, to fluids, it starts to discolor. Coffee, tea, thermal cycling. People usually don't think of thermal cycling, but oftentimes when you're eating dessert, you have coffee and ice cream or some cold dessert, and you're actually thermal cycling your teeth and your restorations while you're having your dessert. Another big problem with composite resins is the fact that they tend to wear away. Even the newer materials tend to have more problems with wearing, and they aren't very stiff. So as we get to large restorations, as the patient chews on the material actually starts to deform under the stress, and that can create sensitivity problems. It can also create bonding problems with bonds starting to break between the material and the underlying tooth structure or whatever you have to try and bond the large composite resin to. Now, I was at the Chicago Midwinter meeting, and there was a fixation with strength in dentistry. I used to be fixated on strength. Long before we came up with Enamic, I started to change my mind and thinking that strength is not necessarily the one criteria that we should be using. That I think we should be looking at load to failure or capacity to withstand stress, using test samples that actually look like real restorations that we're going to use in the mouth. When we do strength testing for our materials now, we make sure that the finish is the same as it's going to be in the mouth, because it doesn't make sense to make these highly polished mirror finish samples, because that's not what's going to happen in the mouth. So here's a chart with pretty much all the ceramic materials that we can have and that we're using. The zirconia is up at the top end, very high strength materials, all the way down to veneering porcelains that go on top of ceramics or on top of metals. And it's not really very meaningful just looking at megapascals. What you need to do is start combining the megapascals with clinical trial data. And for ceramics, the higher stress you're going to put on it, the stronger they generally have to be if they're a pure ceramic material. However, processing is very important, and how you treat the material when you are placing it in the mouth is also very important. So we have zirconia up here. If you look at some clinical studies, it really has to be about 800 megapascals or so for the strength to be sufficient for a stiff ceramic. As we go down, we get different application areas for these materials. We have in-ceram materials, we have alumina, Emax materials as far as cementing. Now we go down here, our original monolithic block, our VITA Mark II, even though the strength value is very low compared to a Bruxer zirconia, let's say, when we bond these restorations into place, and if they have adequate thickness, then the load-bearing capacity is sufficient to work just as well in many cases as a zirconia material. What's also very interesting is that if you start looking in the literature and your criteria for materials is just strength, human teeth are not sufficient with respect to strength to be used in the mouth. So the conclusion that we must draw is that we must extract all teeth and replace them with titanium implants, because we all know that implants are much, much more reliable than teeth. At least that's what I hear from the implantology people and at the school. Of course, the endodontists have a completely different opinion. They think we should save every tooth. The periodontists who used to like to save teeth now are in favor of ripping them out and replacing them with implants. So if we use our strength criteria, human teeth are not strong enough. And here's the reference down here if you'd like to look it up. So if strength is all that matters, why don't we use zirconia for everything, make our houses out of it, our cars out of it? Because materials that are ceramics are still brittle. So even though they may be very strong, when they start to move, when they start to flex, then you have problems with fracture. Now, when I first moved to Boston, the John Hancock Tower was having lots and lots of problems. So you see it here, nice and shiny. The windows are beautiful. Here, this is a black and white photo from one of the newspapers, the Boston Globe. And this looks like it's sunlight reflecting off of the windows, but it isn't. It's actually plywood. When the Hancock Tower was first put up, windows started to pop out of it and crash to the ground. They had policemen stationed by the Hancock Tower. The whole place was police taped off, and only a certain entrance you could go by so that you wouldn't get hit by falling windows. But what they found out was that above a certain wind speed, the tower starts to move enough so that these windows are flexing, and what happened was that they used a very stiff bonding agent between the window and the, actually they had a stiff encasement on the window and the structure. So what they did is they changed the way the windows were placed and used a little bit of a resilient bonding agent, and that solved all the problems. So now we can walk by the John Hancock Tower without having to look up and worry about a window crashing on our head. And if you start looking in the literature, you see that there are also lots of issues with the the jaw flexing. So when you think of making multiple unit restorations, jaw is always flexing, and this is actually a very interesting paper. Has some interesting discussions about, again, implant restorations and what types of materials should be used on top of implants, or when we're joining multiple implants together with stiff materials like a zirconia may be a problem. So exactly what is the difference between strength and load-bearing capacity, which is what we really are concerned about when we're making restorations in the mouth. Strength is kind of an abstract thing that we do. There's a whole bunch of standards that people get together and make. In this case, the standard is making a bar out of your material. Here we have a bar of a dental ceramic. Here we have a bar of concrete, and all the standards have different sizes for your bars. In this case, it's only about 1 millimeter or so, 1.5 millimeters thickness. We know the load at which it breaks, and we know this bar geometry, so we figure out a strength, something called megapascals. What I think we really should be concerned about is load-bearing capacity, which is measured in newtons, but it's just a load-bearing capacity when we make restorations the way we're going to use them in the mouth, the same thickness, the same geometry, as we're doing very complex things in the mouth with very complex structures. So we also do these load-bearing tests, and in my opinion, I really think that the load-bearing tests are becoming more important than the simple strength test, because if you look at this on a strength basis, you can be deceived very easily. So a dental ceramic is only 120 megapascals. Concrete is only 10 megapascals. But if you look at the load-bearing capacity of this thickness of concrete, it's 25,000, whereas that of our dental ceramic here is only 30. So load-bearing capacity, I think, is what we really want to be focusing on, and not strength. Everybody tends to focus on strength. We do a lot of load-bearing capacity tests. This happens to be one where we're looking at PFM and bonded crowns. We usually do them in water because obviously they're going to be in the mouth. You can also thermal cycle them, so they go from 5 degrees C to 55 degrees C, and get an idea of how these materials might survive in the mouth when they're being used the same way you're going to use them in the mouth. A very interesting demonstration of, again, how strength is not the be-all and end-all of materials is looking at a study that was testing the material's reinforcement of natural tooth structure. So what this study did was they took a bunch of natural teeth, they basically crushed them, and you got a load to failure of around 2,000. They restored natural teeth with various pressable materials with different strengths. You see the Emax press at 360, and they also restored it with a monolithic Empress CAD crown as well. And the monolithic material that was bonded in, even though it's much weaker than the Emax press, which was also bonded in, gave you a very high value for the monolithic material compared to the higher strength material. So again, we focus too much on strength and not enough on actually how these materials are used. And we have some very interesting data that was correlated, or excuse me, gotten from testing from various German universities that corroborated some of the stuff that we found and VITA found. But these were from German universities, completely independent. They had no interest in how the values came out that really show the power of the anemic structure. Again, this is a hybrid ceramic. It's not a traditional ceramic. It's not a composite resin. Composite resins look like this. This is an MZ100 material, actually. These are various filler particles that are all surrounded by polymer. So your cartoon diagram, the little white things here are your filler particles. The blue is your polymer. Composite resins, 2 phases, separate phases, very resilient, flexible, too flexible, also tends to wear away. Ceramics, interestingly enough, if you look at the basic structure, looks very similar. Instead of having a polymer surrounding our crystal particles, we have a glass. Again, separate, discrete particles surrounded by glass. Very stable material, but too stiff, tends to fracture when it starts to move. So the idea was to try and combine the properties of both of these, and that was done by creating a ceramic network here that's all interconnected, and a polymer network that is also all connected, and they are connected to each other. So we create a material which is somewhat flexible. This happens to be an indentation. Usually when you indent ceramics, you tend to see cracks. You don't see that here with Enamic. And you have all of your ceramic particles in the yellow here that is connected, and all of the polymer in the blue connected, and all connected to each other. How is this made? Well, it's made initially by creating a ceramic sponge-like network. And this is actually a piece of coral. Coral has an interconnected porosity like the structure that we're creating for Enamic. Coral is actually heat treated and has been used for many years as a bone substitute. It has the right porosity that bone cells apparently like to crawl into and attach to, so it's still actually being used as bone augmentation material to this day. So what happens is the powder particles that we're using are pressed into a block. It's fired in an oven, and all these powder particles grow together, sinter together, so that we have an interconnected network like our porous sponge, and this is actually an electron micrograph of that interconnected network. You see all the ceramic essentially is connected to each other, and then all this porosity is also connected. So if you jumped into a pore, you could walk around. I don't know how many hundreds of years it would take you to find your way out, but eventually you could find your way out on the other side if you jumped into the pore. So we have this porous ceramic sponge network. It's then placed into a monomer material. The monomer goes into the pores, completely fills all this porosity, and then it's cured under high temperature, and we have a chemical bond between the ceramic network and the polymer network, and we have all this material interconnected. So what do we have? We have our ceramic by volume, 86%, and volume percent is how you really want to look at these structures. I know manufacturers often talk about the composite resins about having 86% or 85% ceramic. That's by weight. The ceramic weighs a lot more than the polymer, so it's easy to get a very high number when you're talking by weight. It's not easy to get a very high number when you're talking by volume percent. So you've got most of the material of Enamic is a ceramic with a small amount of polymer to give it resilience, improved machining properties, improved homogeneity, able to mill it to thinner structures than you would get with a traditional ceramic. Part of the initial thought process was to try to mimic natural two-structure. And if you look at a dented material, it's an interpenetrating phase structure, a double network hybrid of a ceramic, which is hydroxyapatite, with a polymer, which is collagen. And years ago when I was working at Harvard as a student, we also had to do a research project as a dental student. Because we're Harvard, we have to do research no matter what. I was looking at bonding studies, and really most of the bond that occurs between the dentin bonding agents is with the collagen and not necessarily with the ceramic. So this is an interesting first iteration of what a natural two-structure would be. We can vary the amount of interconnection and create different type properties. We could also eventually use different ceramics to come up with different materials with different applications. So again, I'm not always going to stress this. This is the interconnected network of ceramic. It's all connected. It's not individual particles that are free-floating. It's all connected. The polymer is connected, and the polymer is chemically bonded to the ceramic. And that was one of the issues during development. Would there be a debonding of the polymer from the ceramic? We did many tests, boiling tests, aging tests, thermal cycling tests, and there wasn't this debonding. Because this was a completely new material, it ended up being a very long development process. There was lots of discussion about properties, and that's one of the reasons why it took so long to get this material out there on the marketplace. So again, if you look at a feldspathic porcelain, individual particles, this happens to be the lava ultimate, which is supposed to be a nano composite material or a nano ceramic. This is a 10 micron scale bar, so some of the pieces in there aren't exactly nano, but there are some nano pieces here. Usually nanoparticles don't want to stay nano. They tend to clump together. It's very difficult to make a truly nano particle material. But you can see the particles are all individual, and they're all surrounded by a polymer. If you look at the volume percent of the materials. Dentin, depending upon where you are in the dentin, it's again an interconnected hydroxyapatite network. With collagen, Enamic is 86% interconnected. And then if you look at a conventional composite resin, maybe like a direct fill, you're between 45 and 50% discrete particles. All the particles are individually, and they're all surrounded by polymer. Lava Ultimate, which was an improvement over the MZ100, is still only about 65% discrete particles. So again, you still have a material where the filler is surrounded by a polymer. It's not interconnected like a natural tooth structure or the Enamic material. Now, our sound wasn't working for Harry Potter, but Harry Potter, my daughter likes to read about Harry Potter, read Harry Potter books and watch the movies, and some became interested over the last year or so. And I was watching one of the movies with her, and there was an interesting clip which shows you the importance of having a ceramic network. Our sound isn't working, so I'm going to narrate it. Harry Potter's always in trouble. In this case, he was in another Quidditch match where he's flying around on his broom trying to catch the golden snitch, the flying ball. It sounds ridiculous when I talk about it. But he's trying to catch this golden snitch, and of course there are evil people always trying to kill him. He gets knocked to the ground and he breaks his arm. So he's broken his arm, and then all the other people are coming over. This is an incompetent wizard, who is the wizard who always does the dark arts. The dark arts wizard never survives more than one film or one book. And his arm is broken, and he's going to use his powers to try and fix his arm and mend the bones. Unfortunately, he's completely incompetent, but he will zap the arm, and let's see what happens to the arm. It's clearly has no ceramic backbone. The backbone is gone. It's not broken anymore, obviously. There's no bone, unfortunately, in there, and it's very highly flexible. So we've gotten rid of the bone problem, but now we have a high flexibility problem with Harry Potter's arm. And therein lies a lesson for us when whether we should be concerned about a ceramic network. Composite resins do not have a network. They have a filler. Years ago, fiber-reinforced network materials were very popular. There was Bell Glass, Art Glass, which was supposed to be the future of restorative dentistry. Didn't work out so well, ended up in a lawsuit. Targus Vectris and MZ100 were all studied by CRA, and they made composite resin crowns out of them. One of the big problems they had with all of the materials was sensitivity. And composite resins just don't have an adequate stiffness to resist stress when you get to very large restorations. They tend to flex under the stresses in the mouth, and they tend to pump fluids in and out of the dentin, which causes sensitivity. The other problem that happens is they tend to flex enough so that you may get the bonding of that restoration off of the underlying structure. So you have lots of stresses as this restoration starts to flex. As you're chewing on it, fluids go in and out of the dentin. That creates lots of pain. And you also start to open up the margins and the bonding layer in between the composite resin crown and the actual cement. Often it comes off clean. The cement doesn't adhere to the composite resin crown, and it'll pop off as these stresses occur on the material. The other problem is it has a very large thermal expansion coefficient. So as you're eating ice cream and drinking coffee, you get a similar effect where the crown is expanding and contracting with the different temperatures. One interesting property of Enamic is that the elastic modulus actually falls within the value of dentin. So actually when you bond a material like Enamic, which has a very similar stiffness value or modulus value to dentin, you get an overall structure which is very resistant to stresses that are being placed in the mouth. As you go to the composite resin side, they're too flexible. As you go to pure ceramics, they start to become too stiff. And again, this was an item of very heated discussion among all of us in the development team where we should be shooting for. Eventually, we all agree that we should be in the dentin modulus area. If we start to get too much above that, then we get to something that's too stiff. And again, we have problems with the ceramic. The interesting thing about this material is that by adjusting the ceramic network, you can adjust the properties. And there are other applications for this material such as implants, abutments, and implants and denture teeth, where we will be able to adjust the interconnection to tailor the material properties for the exact application that we want. This is really just the first iteration or the first offering of this, this material. A good example of the stiffness of the material, testing it, is doing this indentation testing. And this is actually a diamond with a very sharp point that gets embedded or pressed into our material down here, and it creates an indentation in the shape of the diamond. So it's like a diamond. And with a ceramic material, conventional ceramic, you tend to get cracking at the edges of this indentation, and the cracking tends to proceed through the material for a fairly great distance. If we do the same thing to enamic, you don't see the same type of cracking damage that you get with a conventional ceramic. There is some cracks that are developed here, but the way the network is connected with the polymer and the ceramic, you get some branching of that cracking, and eventually the cracks stop at the polymer. So if we start to take a look at where the indentation is, this is the apex of one of the indentations. We see some crack occurring here, some branching occurring as the crack tries to go through the material and cause it to fail. Energy is taken away from the crack, and eventually the polymer tends to absorb the energy and completely stop it. And this is a similar effect that you see with zirconia, where we have our transformation toughening taking energy away. So even though you may have a defect in your material under stress, under natural use in the mouth, the crack doesn't go all the way through it, and then we don't have the catastrophic failure of the patient calling you at 10 o'clock at night. They have some event to go through the next day. They just bit down on something and their ceramic crown cracked in half. That's a catastrophic failure. You won't tend to see that with materials like this, which can stop the cracks from propagating through the material. Lots of natural teeth out there, lots of natural teeth with cracks in them. The idea is that even though you might generate some damage in the material over time, that material is damage resistant, so it lives another day. It doesn't have that catastrophic failure. And here's a bend bar over here. It's only 0.2 of a millimeter thick, and this is something you can never do with the ceramic, and it would have been cracked into many little pieces by the time it reached that flexure value. Another geeky type of thing that ceramic people like to look at is something called a Weibull modulus. And why is that important? Because it's actually a measure of how reproducible and reliable your material is. If you have a high Weibull modulus, your material is going to tend to be very reproducible and fail around a narrow range. If it has a low modulus, then it can fail anywhere across a very wide range of values. So let's say we have a material that has a load-bearing capacity of 1,000. If we have a high Weibull modulus like 20, our material, most of the restorations that we make or material that we make out of it will fail right around 1,000. Maybe it'll be 950, maybe it'll be 1,050. That's not going to be a big spread. If we have something with a low Weibull modulus, say under 5, if our material fails, it might fail at 1,000. It could fail at 500, could fail at 1,500, and there's going to be a very wide spread of values there. So you may be the unlucky person that gets the material that fails at 500, or maybe you're the lucky person that gets it to fail at 1,500, but there isn't a lot of reproducibility in that material. So if we look at a comparison of the Weibull modulus of enamic versus other materials, and actually this data that was generated by VITA is almost exactly the same as data that was generated by 3M, and this is an abstract that's being presented at the International Association of Dental Research in a few weeks out in Seattle. So if you look at the Weibull modulus of enamic, it's around 20. We have different iterations that we can get up to 40, which is just incredibly geeky, exciting stuff for ceramic people, because you never get something that high unless it's a really, really, really bad material that fails at a few megapascals. Emax is under 5, so you have a very wide range of failure for that material. Empress CAD and Lava Ultimate are also under 10, which means you get a fairly wide spread failures for that material, you don't really have a highly reliable, reproducible material. Everybody was surprised at this value too. It was another surprising thing. Again, we said we wanted to have a material in between ceramics and composite resins with respect to wear behavior. So this was a test done at the University of Tübingen. They like this wear test over in Europe. We had lots of fights over wear tests, and I mean fights over wear tests. So we did our own wear test, VITA did their wear test, and they had a third wear test done. And also Professor Merman looked at wear in the mouth. So we had lots of contributions to the wear issue and lots of heated discussion. So what this test does was basically look at how wear kind the material is by measuring enamel loss and looking at how resistant the material is to wearing itself. So we have our composite resin in red, enamic in green, and our feldspathic ceramic in blue. So let's look at the enamel loss here. If you have a higher bar, that means that you're wearing away the enamel faster. So the material that wore away the enamel the most was the feldspathic ceramic, then the composite resin, and then the enamic. But if you do the stats, these two are the same, and the ceramic is higher than these two materials. Now let's look at material loss, which is a problem with composite resins. You see the composite resin lost the most material, so it's not a very stable material in the mouth as far as wear goes. You look at the enamic and the ceramic, they're basically the same, and they are significantly less than that of composite resin. So indeed, in this test, it shows that we are in between the worlds of ceramic and composite resin. We have a material that is wear kind, it doesn't destroy the opposing dentition, and we have a material that's very stable. It doesn't lose thickness during wear testing or theoretically in the mouth. And so we are in between both worlds of materials. We've done our own wear tests. We have wear tests with human enamel, where we make pins out of human enamel, and we run it against the material. In this case, we're making pins out of Mark II because we're waiting for another batch of teeth to come through. It's not easy to get teeth extracted that are acceptable for a wear test. They have to be freshly extracted. So it's not as easy to do. We're waiting for some more human teeth to come around. So in this test, we were looking at the groove depth that was created in MZ100 and Lava Ultimate and Enamic. This is a higher groove depth. So the higher the groove depth, the more it means that the material itself is wearing away. So if we look at the material wear itself, the MZ100 is very high. The Lava Ultimate, yes, there was a significant improvement, so 3M did make an improvement in the Lava Ultimate. However, the Enamic is statistically and significantly better than the Lava Ultimate or the MZ100. If we look at the material weight loss, we have a similar situation where the MZ100 was the worst, followed by Lava Ultimate, and then Enamic, a very small amount of weight loss, significantly better than either of the two materials that we were looking at. So again, it behaves much like a ceramic with respect to wear resistance. We look at color stability, which is another issue with composite resins. And the yellow is Mark II. This weird reddish color is the Enamic DNH double network hybrid. You then have a composite resin in this kind of aqua color, and then temporary bridge resin in this bizarre pinkish color. Things look very strange on my screen. Now, most people can see a color difference when you get to a delta E of between 2 and 4. If you can't see it when you get to 4, then you better have someone else taking your shades for you because you're in trouble. And these are a variety of tests that people use: water, coffee, ultraviolet light, thermal cycling, and thermal cycling followed by coffee. Now, why do we do this? Well, for materials with 2 phases, like a composite resin or the enamic material, there may be an issue of the polymer separating from the particles, and so that eventually you'll get percolation in between the particles and the polymer, which would be highlighted by this coffee, the dark coffee going in between the polymer and the particles. This is really a very good stress test on material to see how well there is a bond as well between the particles and the polymer, because the coffee will go in between those two if they start to debond. So Look at water, everything was okay in water. Coffee, composite resins, you saw a color change above 2. Ultraviolet light or acrylic material was really bad, so you don't want to keep people in temps for very long. Thermal cycling, we're just at the level of being able to see it in a composite resin, but thermal cycling in coffee really highlights that issue between the particle bond and the polymer and composite resins, and you see that huge change in the color of the material, whereas for Enamic over here, basically the same as Mark II, like a ceramic. Loss of gloss, this was Professor Merman's big concern, and again we had reformulations based on Professor Merman's input, both with respect to wear and loss of gloss. So I don't have the exact means of his aging. I'm waiting to get that information. But he has an aging study, so we started off with the polished materials here in blue, Mark II, our Enamic hybrid ceramic, Lava Ultimate, and MZ100. Looked at the change in gloss after aging, so Mark II got a little less glossy. Hybrid ceramic lost a little bit more gloss than the Mark II, but was higher in gloss retention than the Lava Ultimate, and all of these materials were much, much higher than the gloss retention in MZ100. So again, we're kind of in between a ceramic and a composite resin. Load-bearing capacity, and this is a very interesting study. We have our own studies that corroborate Dr. Fisher's work. And in this case, you're taking restorations, milling them out to 1.5 millimeters thickness occlusally and 1 millimeter thickness radially, bonding them to an underlying substrate that's like dentin, and then doing the load-bearing capacity. So if we look at this test, the Enamic is yellow, Emax in red, Lava Ultimate in the pink. Essentially, when you do the statistic analysis, basically these are all the same. The Enamic did have the highest mean strength, load to failure, but if you do the stats, because of the spread in these other materials, essentially the statistics show them to be all the same. Mark II was lower, and so was Empress Cat. Now, the really interesting study that we didn't do and VITA didn't do, they contracted this out to Dr. Goose at Freiburg, and this was a chewing machine test in which the crowns were made at different thicknesses. They were bonded onto a substructure, again, that has the same properties as dentin, and they were placed in water. They were thermal cycled between 5 degrees C and 55 degrees C, so you get a very big change in temperature. You're also chewing on it with almost a 200 Newton load, which is a very high chewing load, and ran this for about 1 million cycles. And they like to do millions of cycles over in Europe. And the endpoint was to see how many survived this onslaught of thermal cycling and chewing stress in water during the test. For Emax, only about 50% survived. For Enamic, and when you do 3D, it doesn't work exactly right, but Enamic survived 100%, and this was comparing 1.5 millimeters occlusal thickness and 1 millimeter wall thickness. Now, when they went to a thinner occlusal thickness and wall thickness down to 1 millimeter, you've also got 100% survival. I don't know exactly how thin you can go, and VITA doesn't recommend you go that thin, but you can look at the data and make your own decision. You can mill it very thin. You can mill the margins very sharp. Like I said, we don't exactly know how thin you can go and still have a success, but at least in this lab study, again, done independently of VITA and myself, even at this fairly thin value, you still got 100% success after this highly stressed test that was done. Milling behavior. It's very fast, efficient. Now, you have to have the right software that has the right milling parameters for Enamic to get these times. If you don't have the new software with the Enamic in there, then you won't see these type of milling times. This was done by Sirona. So you see the milling times in the fast mode, Schnell, and the normal mode, normal. Then you compare it to other materials in this list. You see it's very fast, a crown, 5 minutes in the Schnell mode, compared to Lava Ultimate in the 8 minutes. So you may wonder, well, Lava Ultimate also has a lot of polymer in it. Why isn't milling as fast as Enamic? A polymer material should mill fairly quickly. the diamonds actually become clogged with the high polymer content in law of ultimate, whereas in the enamic, the polymer helps facilitate the burr cutting through the material, and then the ceramic network facilitates cleaning out the diamond burr, so it actually sharpens the diamonds as it's cutting. So you've got, again, best of both worlds between the ceramic network and the polymer. What was really shocking is how many blocks you could mill with a single set of burrs. So this again was done with Sirona. They stopped at 150. I guess it was the end of the day. If you've ever visited a German company, when the whistle blows, everybody runs out of the building. It's a lot different than over in the U.S., where even if the whistle blows, if you're still running an experiment, you finish the experiment. But in this case, it was the end of the day, and they got to 150 blocks for the normal mode on the MCXL, and they stopped. They did it in fast mode as well. This is 130 blocks for one set of burrs. I know in the clinic we have a variety of milling machines. Even though it says 30 blocks for Mark II, I think we're usually at around the 20 blocks for a single set of burrs with our Mark II materials. And Emax down here at 18 and 10 for number of blocks you can get for a single set of burrs. So this is maybe the most stunning result as far as milling behavior with respect to how many blocks you can mill on a single set of burrs. Another demonstration is when we mill out veneers with Enamic versus Mark II, Empress Cat and Emax. You can clearly see the chipping that occurs in all the traditional ceramic materials, whereas you don't see that for the Enamic. You can make very thin veneers, essentially no prep veneers, milling Enamic on the Ceric system, whereas obviously you can't do that with any of the traditional ceramics because it just gets too thin and it chips severely. Another advantage of the Enamic material, if we're looking at versus lava ultimate, is bonding. Now, I was at the Lab Owners of California meeting, and a lot of the things they were talking about with respect to lava was debonding. I don't know if people have seen that as an issue or not. At least these lab people were talking about it. With Enamic, you have this interconnected high-density network of ceramic, etch-it, silane, bond like you would any type of ceramic material, with a highly filled composite resin. With the small particles, it's a combination of glass, silica, zircon, which is a zirconium silicate, which is kind of like a glassy combination with zirconium, and zirconia. So some of the particles you can't etch at all. Some of the particles, like the glass particles, will etch away completely and dissolve completely in your acid. So you're trying to bond to a very highly cured polymer. And that's one of the reasons why cojet is recommended, if you look at the website, to try and embed silica particles in the polymer so that you can bond to them with silane. VITA is recommending acid etching for 60 seconds with 5% hydrofluoric acid. If you have an 8% hydrofluoric acid, then you cut that down appropriately. Everybody has different acid strengths, so you have to look at the strength of the acid, just like you would if you're bonding in a porcelain crown or ceramic crown. Depending upon the acid concentration, you need to adjust the acid etching time. Some clinical cases, and overall, VITA's has clinical trials going on for probably 3 or 4 years, somewhere around there for many of the restorations. They say they haven't seen any failures. They say that in previous materials that they've tested, they've always seen failures occurring at this stage, but they have not seen any failures, and it's been on a variety of situations: implants, crowns, onlays, inlays, veneers. This was a case presented by Dr. Pricer at 27.5. She had a patient with Amelogenesis Imperfecta. There was no material that they could think of that would work very well for this patient. They heard about the material from VITA. VITA donated the material. They milled it in a very challenging situation down to 0.3 millimeters in the grooves, only a millimeter at the cusps. Bonded it on to the patient's teeth. From this perspective, even though we might not think the aesthetics are very good, the patient was ecstatic in how they looked versus what she was walking around with for most of her life. They even stressed it more by putting brackets on top of it. This was at 1 year recall. It's about 2 years now, and according to Dr. Preissner, they're still going well. At 0.3 millimeters, your ceramic would have cracked, and your composite resin most likely would have been worn through at this stage. So this is a really challenging case for this material that's survived so far very well. Dr. Skramstad, and thank you for sharing this case with me. I have been battling pneumonia for about 6 weeks. Unfortunately, as soon as the material was approved by the FDA is pretty much when I got sick. And if I was in the clinic working on my patients, unfortunately I was worried that the burr would go through the maxilla and into the brain, and that would be a very bad situation for everybody concerned. So fortunately, I haven't done many cases with the Enamic myself. In the next few weeks, I'll be back into the clinic. So this is replacing an amalgam which is one of my least favorite restorations, not because of mercury, because it does nothing to reinforce the tooth, and actually, in my opinion, weakens the tooth greatly. And we overuse amalgam and undercut the tooth structure. And so this amalgam was replaced. You see the chipping and the leakage, as you always see with amalgam restorations over time. Restoration designed, polished. Now VITA has a specific polishing kit that you can ask the VITA people that's designed to match very well with the Enamic properties to give you a quick polish in a very short amount of time. There's other polishing materials you could use, but for now, I'm recommending the VITA material. Again, talk to VITA. I'm a scientist. I help develop material. All the shades and marketing stuff, that's all has to do with VITA. So this is a very nice result by just polishing the restoration and then bonding it into the mouth. And these are some of the polishing materials from VITA. They have a pre-polish wheel. They have a high shine wheel. They were all developed to be used specifically with Enamic with some diamond embedded particles in the wheels. Dr. Puri, again, thank you. Again, replacing my least favorite restoration, an amalgam restoration over here, which does nothing but destroy teeth over time. And very nicely done, very polished, blends in very well with the surrounding tooth structure. Dr. Conte, looking like we're doing a endo crown. We do a lot of endo crowns at school. Everyone, the older faculty tends to scream and yell and cry like we're doing something horrific. With the endo crown, we have a very good recall system at the school, and so far our endo crowns have been doing well over the past 3 or 4 years. So it looks like there was some buildup here, possibly composite resin or so, polished, bonded into place. Some cases from VITA. This is not recommended for use right now. This is actually an implant crown that was a screw-retained crown. Benedict Genoyan, who was in Chicago, and Dr. Balzer out of Switzerland. So they have their implants. You can tap this very well and create very nice screw threads. We put it on the drill press at BU just to fool around with it and see how it might be used for implant applications. So you can tap it, screw it down, and you're in good shape. One of the strangest applications that I've ever seen, but we have lots of patients like this coming in with resorption and root problems being worn away. We usually slap composite resin or glass ionomer in there, and it never really stays very long. This dentist went ahead and milled out tooth neck veneers. Very interesting application I would have never thought of. Milled them out, bonded them in, polished them up. Now, I don't know whether the patient suddenly discovered the fact that there are toothbrushes out there, but if you look at the gingiva condition, going from this angry, purple, swollen, bleeding case to after the tooth neck veneers, where it actually looks very nice. So either the patient discovered a toothbrush, or in addition to discovering a toothbrush, the fact that this material was replaced over his existing structure and gave him a better contour. Maybe that also helped to provide a better healthy condition for the gingiva. Let me just, I know we're running out of time here, so let me just skip ahead to something that I think is very interesting. Again, this is the no prep veneers, and I know they're very popular at this point. There's a lot of them being done at the school itself. the Serenade system. But with this material, excuse me, you're now really able to mill it with a Cerac, and in this case again from Germany, essentially doing a no-prep veneer here, milling them out, bonding them on, and you get a very nice result here just by doing a no-prep veneer type case. So indeed, as Professor Michael Swain says, he's done a lot of testing it, published some papers on the material. Again, an independent researcher out of Australia, very well known in the material science world. A lot of his work is on zirconia. He's gotten into dentistry the last few years. And did some testing on it and finds it to be a very tooth-like material. So essentially you have a material that has properties like dentin but wears a lot like enamel. And thank you very much. This happens to be Boston from the river when it's not covered with snow in the summer. And this is a building at VITA where they do a lot of research work over there on this material. So I am done for the evening, and I know I took almost the entire time.
That's
so
okay. It's great.
Is that okay? So hopefully questions will be streaming in, and I guess I will also get on the discussion board at some point and try to answer those as well.
Hey, Russell, so if anybody has any questions, you can just type them in, and we'll kind of send them forward. We just have a few minutes left here. But one of the questions that came in, Russell, was you showed the case that the restorations were milled very thin, 0.2, 0.3 millimeters. What would you feel comfortable on a routine basis on a molar? What would you recommend as the thickness? I know we've always talked about having 1.5 millimeter material thickness. Are you comfortable with recommending on an official basis going thinner than that?
I am comfortable going thinner than that. VITA will not say that, but based on testing that we've done and that's been done independently, I think you can go thinner than 1.5 millimeters. How thin you can go, I don't know yet. Certainly that demonstration of 1 millimeter in that thermal cycling chewing study makes me think you can get close to about 1 millimeter. So.
Great. The other question that is here is there is the glaze that's available or soon to be available for this material where you actually etch the external surface and apply the glaze. Could you talk a little bit more about that?
Right. So the glaze is basically like a composite resin type material. The etching of the surface, again, because you have such a high ceramic content, gives you an excellent bond between the glaze, stained glaze combination, and the surface of the enamic material. How long it's going to last, I don't think anybody knows. We know that stains and glazes that are used on top of ceramics generally tend to last about 2 to 3 years. There are a number of studies that were done with Empress external staining and glazing by Dr. Scherer, and you start to see a color change after about 2 to 3 years depending upon what the patient's doing. Now the advantage of enamic is that you could re-etch it and restain and glaze it, where with the ceramic, when the glaze wears off, you can't stick the patient's head in an oven and reglaze it.
Very good point. You certainly wouldn't want to do that.
No, you wouldn't want to stick the patient's head in an oven. That would be bad.
Okay, we have a couple more questions that are coming in on the written questions, Sam. Do you want me to ask them?
Yeah, why don't you go ahead and ask them, Liz?
Okay, so I've got Dr. Hickman asking, how does the strength compare to Emax?
Okay, so in those 2 slides that when we did the testing of the crowns, the stress resistance was the same as Emax, and just doing that static load where you just basically bite down on it. When you do the extended testing where you're doing a chewing system, the Emax failed. About 50% of the crowns failed, whereas 100% of the enamic restorations survived the test. So essentially, it's you get basically the same load-bearing capacity in a standard test, and you get a better survivability based on those tests that we saw with the enamic than the Emax.
Okay, thank you so much for that. Yes, Dr. Schill, everyone will get a copy of this presentation because we're recording it, and I will email out the recording to you. Okay, can you use monobond instead of porcelain etch? That's from Dr. Boyle.
Can you use monobond instead of porcelain etch? I've been using the Ivoclar multi-link Automix, and I've always used a separate porcelain etch with it. So I am not sure. I'm not going to answer that question because I just don't know.
Okay. And then I'm going to ask one more question here. There's a lot of questions at this point. Do you have a specific bonding system that you do recommend from Dr. Vale?
Okay, so VITA is recommending the Reliax material from 3M. I'm recommending the VITA Multi-Link Automix, essentially because we've been using that with all of our restorations, and you've got a very nice bonding to zirconia. You can bond to metal, you can bond to porcelain. In my situation, working with residents, we get everybody on the same page so we don't have anything messed up in the very important step of bonding the material.
All right, great. Hey, so
yeah, let's make sure, if you all want to ask more questions, you can go to www.sericdoctors.com/VITA, and that's going to take you to a landing page where you can click to go to the official discussion board thread that's going. You can ask all these questions there, and Dr. Giordano, Dr. Puri, all of our staff will be on there, and they can answer the questions as best they can.
thank you, Dr. Giordano, and thank you, everyone, for joining us. We appreciate you joining us on this webinar, courtesy of sericdoctors.com and VITA. We look forward to seeing you on the message boards, and remember, we've got videos on all of this stuff, and this presentation, if anybody wants to review it, we'll have it archived for people that were on this webinar, so that you can review the information presented by Dr. Giordano. The blocks are available. You can order them through Patterson Dental. And thanks for joining us, and have a wonderful evening.
Thank you.
Thank you.
Thanks, Dr. Giordano.
You're welcome. Thank you.
Bye-bye.
Bye.